I don't want to say that. Essentially, this is principal ideal.
Well, the kernel's not zero because
Or sorry, it's generated by that single polynomial because it's principal ideal.
right.
But this was a map of, I think, A vector spaces. So how do you know that the kernel actually looks like an ideal inside of the polynomial instead of it?
Because for a PID, that's precisely what the subspace is. Well, I'll go through that detail.
Okay.
Okay, other questions before we start? So actually, this will directly deal with Jack's question here. So last time we had let me keep my notation here. The and remember, E was an n-dimensional vector space over K, and Kx is of course a polynomial ring. B is a homomorphism or a linear transformation from E to E. So this is fixed. So input linear transformation, output, well, I'm sorry, input polynomial up here, output is a linear transformation, right? By applying whatever polynomial, right? So just to be clear, if f of x is a0 plus a1x plus a k x k, then f of v is equal a0. That's the identity. And this is pretty easy to see as a linear transformation, right? Because compositions, this power of phi is a composition, and since it goes from A to E, I'll composition to E. Everybody okay? Now, notice that as K vector spaces, the dimension of this guy is infinite. The dimension of this one is actually n squared, in particular less than infinity. Right? So, by the way, I didn't verify that this is a linear transformation actually, but it is. It's fairly easy to justify that. So the kernel, which is the set of F, such that F the zero transformation, cannot be zero, right? Because this is infinite dimensional, this is finite dimensional, so there has to be some non-trivial kernel. Notice that kernel is a right. I think it's probably clear enough. Why is an ideal K of X? I think it's pretty clear that if you have F and G that are in the kernel, then so is F plus G, right? So if F and G are in the kernel of so F plus G is in the kernel. Right. And if K of X is in capital K of X and F of X is in the kernel, then K of X times F of X kernel. Because what is how does this thing work? Well, if you look at this is K times F C, which is so this is factor 9, right? And this is the rub as Kx is a principal ideal domain. Is generated by a single polynomial. Right. It's of course it's not 0 because the kernel is not 0, but that's the important thing. This is a principal ideal domain. So this plays the role in theorem 722 of that Q sub phi. Of course, Q sub phi of phi must be 0 because it is in fact in the kernel, and Q phi must divide every polynomial that has that property that annihilates that. Okay, any questions so far? So the proof for the matrix part is very similar. I encourage you to do that as well. The linear transformation part actually might be a little bit tougher to see. We'll make the following remark. Q of phi is called the minimal polynomial for a linear transformation phi, right? Because in fact, if you think about the role it's playing over here in PID, it is the smallest degree polynomial that has this property. So that's why it's called minimal. And from the other part of the theorem, QA is minimal polynomial. For matrix A. Let me do kind of a quick example here about the difference between this is probably something you've seen, but I don't think it's going to hurt anything to kind of look at it before. Let me give you kind of a simple example. Okay. Let's look at these three matrices. Do y'all remember what the characteristic polynomial is for a matrix? It's what you did in linear algebra, the polynomial that you use to find the eigenvalues, right? And you've probably seen the what is it? Cayley's theorem, I guess it is. That every matrix is annihilated by its characteristic polynomial, right? Everybody okay with that? Now notice these all characteristic polynomial. Well, what is the characteristic polynomial of this matrix? And this is actually true for all of them, right? Because the determinant of a diagonal matrix, some people might say 1 minus x cubed. I would split that hair. If you subtract the x, that should be 1 minus x cubed, but whatever. The determinant of an upper triangular matrix is the product of the diagonals. So it's fairly easy to figure out that the characteristic polynomial is they're all the same. And of course, if you do, you can apply the Cayley's theorem here, and you subtract 1 from the diagonal and cube this, you get 0. If you subtract 1 from the diagonal here, you get all zeros except this. If you cube that, you will get 0. And if you subtract 1 from the diagonal here, and you have this matrix that has 1s on the super diagonal, and you cube that, you get 0 as well. What is the minimal polynomial? For these 3 matrices? This one is just x minus 1, and you can kind of see this because if you subtract the identity matrix from this, I mean, that's, there you go, you get 0. How about this one?
X minus 1.
Good. You can actually, when you subtract 1 from this, just that 1 up there in the middle top row, when you square that, you get 0. And anyone want to take a guess here?
X minus 1.
Right, if you take a matrix that has these ones on the super diagonal, this will, you have to cube, or you have to take this to the 3rd power to get 0. So notice in this case, the characteristic polynomial, the minimal polynomial is the same, but here the minimal polynomial is smaller, which is a possibility. Notice that the minimal polynomial divides the characteristic polynomial, and that's what that theorem says, because the minimal polynomial should divide every polynomial or every polynomial that the matrix that annihilates the matrix should be divisible by the minimal polynomial. Yes.
Wait, sorry, how are you finding the minimum polynomial?
I'm using force. I just happen to know. Well, I'll go through that if you like. So if you look, is it clear to you that the top one has minimal polynomial x minus 1?
I guess I'm not sure. I guess I'm not sure what the minimal polynomial is.
So here's the minimal polynomial is the smallest polynomial with respect to degree that the matrix is sort of a root of, right? Now for x minus 1, I really should be better and call this x minus, because this is the identity for 3x3 matrix. Notice if you plug this matrix into this polynomial, you get the 0 matrix, right? So, and of course, you ain't gonna do any better than degree 1, right? So, we okay with that?
Yeah.
Now, for the other one, that's my claim here. If you look at this, in this case, 0, 1, 0, 0, 0, 0, 0, 0. And so x minus I3 squared. So if you square this matrix, this row times this column, notice the 1 goes across 0. So and after that, you've got just rows of zeros multiplying, so it's all 0. So you may ask yourself, hey, self, deep in the depths of some Stephen King novel, how do you know that there's not some other wonky polynomial that I missed, right? Like a linear polynomial I could have done better with. But here, once again, the ring theory kind of takes care of this, because I think at this point we can agree that the minimal polynomial, so this is a polynomial that this matrix here is annihilated by, right? Now, by our theorem, if you think of this as the matrix of linear transformation, the true minimal polynomial, since this polynomial annihilates this matrix, the minimal polynomial has to divide this polynomial. And the only divisors of this polynomial, right? Because x minus I3, that's a prime, that's a linear, so that's a prime polynomial in Kx, right? The only polynomials that divide that are either 1, which clearly that's not a root of, x minus I3, which it's not a root of. And so this has to be the minimal polynomial. And it's more of the same for this one, only it's a little bit more multiplication, because if you look at x minus I3, in this case, you get this matrix here. Now notice x minus I3 squared is and x minus I3 cubed now you multiply this by this, and you're going to get the zero matrix. So using my terminology a little bit loosely, this matrix is a root of this polynomial. And so the minimal polynomial of this matrix, actually, since this polynomial kills this matrix, the minimal polynomial has to be a divisor of that. But the only divisors of x minus 1 cubed, that's a prime power, that's like a prime cube. The only divisors are 1 p squared p cubed. And you can see from what I put up there that none of the smaller degree polynomials kill that matrix. So this truly is the minimal polynomial. Okay, good question. Any questions? Okay. So now that we've kind of set this up, we did talk about modules over PID. What's this all this got to do? This? Well, we well, let me remind you, phi E, so that is phi is in home K. E. So that's a fancy way of writing phi is just a freaking linear transformation. That's it. So I claim that this induces an R module structure on E. Well, let me see here. Let f of x be a polynomial in Kx. Let E be an element of this vector space E. Okay, I claim that I can use f of x as a scalar, multiplied by E. So here's my input. It's this vector that comes out of E. Here's my scalar. That's polynomial. Somehow I have to use this polynomial and this vector to get a new vector. Any ideas on how I might do this? How might I use this polynomial to get something out of E? And remember, this might be important, phi induces, right? So phi is a tool that I might use. Very good. We already know that this sucker's a linear transformation, right? So just plug phi in, and you get a linear transformation, and then let it act on E. So this is the way to do it. Now, I am going to give you a couple of definitions here. A K subspace. We'll say F and E is said to be phi invariant. By the way, any ideas as to what phi invariant might mean?
By feet is tight.
Right. So you've got this big space E, you got this little space F. We say that F is invariant. It doesn't mean that it fixes the elements of F, but what it does mean, if the image of this subspace under phi stays inside, right? It's like Vegas, baby. It stays in Vegas, right? For sure. That's what the TV tells me anyway. So this is what we mean to be phi invariant. It takes F and it puts it back inside of F. Equivalent. Equivalent to the statement that F is a KX submodel of, right? Because notice that if phi of F is in F, then let me kind of continue this idea. That means phi squared of F contained in phi of F, which is contained in F, and so forth and so on. So every power of phi keeps F inside of F, which means that if phi is in F, then this thing is just a big fat linear transformation, right? That is basically powers of phi, and every power of phi keeps this b inside of F, and so the sum is inside of F. So this is equivalent to the statement that F is. So what it means to be phi invariant is that F is actually, as a KX module, is a submodule of B. Let me give you another kind of terminology that we're going to use. Also, given B and E, so suppose let's just pick some random vector, B and E. The subspace spanned by the set So if you look at V, then you look at phi of V, then phi squared of V, and phi cubed of V, and so forth. Take that forever and ever. We're going to note this. Well, E. E. So sort of a subspace generated by V and phi is a phi cyclic subspace V. Right, proof of this is fairly easy because if X is in E dt, then I can write X as a finite A0, A1. Oops. That's what a typical element of this phi of E phi D is. And if you look at phi of X, this is A0 phi of D plus A1 phi squared D plus AL phi L plus 1 D. And this is still in EV phi. So this is a phi cyclic subspace. Okay, everybody else? Yes, sir.
Does phi cyclic just mean the same thing as phi invariant, or
Well, what it means to be phi cyclic. So phi invariant, okay, I see. Phi cyclic is a special case of phi invariant, right? So if you have an invariant space, it doesn't have to be generated by the linear transformation acting on a single vector, right? So for example, let me give you a silly example. The entire vector space is phi invariant, but may not be phi cyclic, right? You may not be able to find a single vector that does this trick here.
is this like a definition?
Right, yeah. Well, it's it's a notation for the definition, but it's also a statement of fact that when you stand by that, it's a phi invariant. Right. Right. Okay. So let's get to this business here, theorem. So let me write down words, and then we'll kind of sort through this at the end of it. Let E be a finite dimensional vector space. Over K. And phi in E to E a linear transform. Right, and this is going to be similar to there are harmonic polynomials. Yeah, I'm gonna make a couple statements here. Q1, Q2. And KX. And phi cyclic subspaces. Column E1, E2, and P and E. Such that E is the direct sum of these. T. And Q1 divides Q2 all the way up to QT. Put that in the introduction. This probably looks familiar, right? Because what this is this is basically the invariant factor stuff that we've been talking about. Basically, what happens is as a K of X module is a torsion module. And so there's no free part. So we decompose it into a direct sum and corresponding these invariant factors. Let me add a little spice to this. Each QI is the minimal polynomial of the restricted to EI from EI into EI. Notice that when you restrict phi down to EI, the fact that these EIs, the fact that these EIs are phi cyclic means they're phi invariant, and so it should go into EI, right? The collection of these polynomials Q1, Q2, QT is uniquely determined by E and C, and minimal polynomial of phi is, anybody want to guess what the minimal polynomial is? Maybe I can do some guess at it if I do this. That's a finite abelian group, and that happens to be an invariant factor decomposition. 3 goes 2 divides 6, 6 divides 3. Everybody agree with that? Yeah. What is the exponent of this group? Does anybody remember what exponent means? I don't want to be throwing around words. So you know what the order of an element is, right? Yeah. The exponent, you know what the order of a group is, right? The exponent, if it exists, which it certainly will for a finite group, is the smallest positive integer, such that if you, so the exponent of a group the minimum over the set n, such that Gn is the identity for all G and G, or infinity if no such thing exists. So for a finite group, this always exists, right? Because all you have to do is take every element to the order of the group. And the order of this group is, in fact, 3600, right? So certainly 3600 is an upper bound to the exponents. What is the exponent of this group?
300.
300.
This is the LCM of Q and Q.
Right, so what's the minimal polynomial of phi?
LCM.
Right, but they all divide each other, so the LCM is the biggest one. You're right, it is the LCM,
Yeah.
but here it's, they all divide each other, so the LCM is a little bit easier to have your head around. Okay, any questions on that? Okay. There can't be a one without a two, so as you might guess, this first one is the invariant factor decomposition. I'm going to do something similar. I always hate writing down rules of the elementary divisor ones because it seems so obnoxious, but it's really, in practice, it's not any more difficult to handle. Right. Okay. I hate this. There exist monic irreducible polynomials. There exist monic irreducible polynomials. P1, P2, P something, we'll say PS. AX. And phi cyclic subspaces. Bij let's say I between one S and we'll say that J is between one J, such that E is isomorphic to the direct sum I equals 1 to S and J equals 1 to KI. Of the J. And for all I, there exists integers M1. Let's say, I'm going to count down. Two. I sub k greater than or equal to 0. Such that and I guess I could assume that last one is strictly greater than 0. Such that pi mij is the minimal polynomial of phi restricted to Bij. Bij. And as before, these elementary divisors and if it's not clear what they are these things are uniquely determined. by phi. And, okay. So this is just basically our statement about, in fact, what we're dealing with here in this situation, both part one and part two, is we're dealing with a finite dimensional vector space E and a fixed linear transformation phi on it. Now, because the vector space is finite dimensional, this is actually torsion, right? This is actually a torsion KX module, KX is PID. And so basically, this is just exactly what we got when we played around with stuff like this, only it's written in the language of these vector spaces. That's that. Now, let me show you what we get from this. And so I'm going to develop the theory just a little bit, and then we're going to get our hands dirty and actually I will show you how to do this, so to speak. Theorem. So let's first deal with a linear transformation that is in fact phi cyclic. Let phi be a linear transformation. Such that, well, so let me just start that here. I am going to state this in terms of just a phi cyclic transformation. Notice this theorem here talks about a general linear transformation, and then it talks about phi cyclic subspaces. I'm going to show you what the phi cyclic subspaces, how they sort of look. And then that'll be, because all you have to do is glue these things together to get something more general here. So V is phi cyclic with minimal polynomial. With minimal polynomial. Q of X is A0 plus A1X plus, I make this mine, I better make this mine. Yeah. A R minus 1, R minus 1 plus XDR. So, yes, this is a monic polynomial. If and only if the dimension of the entire vector space E is exactly equal to R, that is the degree of that minimal polynomial, and there is a basis of E relative to which the matrix of E is, there is basis of E relative to which the matrix of P is E. And here, let me point out, sort of parenthetical remark, that in this case, E is E, D and D. So in general, we can use this. This is sort of a block for and so you can basically break up a matrix into these blocks that correspond to your whole polynomial, the prime power factors and the invariant factors. Let me give you a, let me describe this matrix too, and I'm going to give you a corollary, and then I'll kind of explain how this works. By the way, do you usually multiply your vectors on the, when you multiply a vector by a square matrix, do you put your vectors on the left, so it's a row vector, or do you put it on the right, it's column vector? That's me too. I usually use column vectors. This is actually set up for row vectors on the multiplying on the left, and I'll show you what. And you know, I find it a little obnoxious too, but this is kind of most of the places you see this. This is the way you write it. If you wanted to use it with multiplying column vectors on the right, you'd have to take and transpose this actually. But this is a fairly simple form, right? Because what you have is you have zeros everywhere except for ones on the super diagonal. And then across the bottom, you basically have the reverse sign of all the coefficients that come before the highest degree term. Let me give you a corollary. Like I said, this is used for what we call the primary rational canonical form. Here's a corollary. But most of you had said that you hadn't heard of the rational canonical form, but you all had heard of the Jordan canonical form, right? Or at least that's, you know, some you've heard around the campfire anyway. So let phi from E to E be a linear transformation. Of V over K, or of E over K, the linear transformation. Then E is phi cyclic and E has minimal polynomial. With minimal polynomial, X minus lambda to the R notice that in this case, in the original theorem here, I had sort of an arbitrary. Don't really need to know how to factor it. For this corollary, I need to know how to factor it. I need to know that my polynomial for the phi cyclic one is actually a linear polynomial to the rth power. It has to be linear. So in other words, that lambda actually has to be in the field K. With minimal polynomial of this, if and only if m b is equal to R, and there exists a basis for it relative, which the matrix will be is Round up 1, 0, 0, round up 1, 0, 0, 0, 1, 0, 0, 0, 0. 1, 0, 0, 0. So in other words, this is a matrix that is all zeros except for it's got this root, this eigenvalue, lambda, on the diagonal, and it's got all ones on the super diagonal. This is called Jordan form. It's Jordan block. Now I'm going to briefly explain why this works and my mysterious remarks about left vector and right vectors here. And show this corollary. And next time we're going to really get our hands dirty and work on this. I'm going to do a number of examples. So, any questions on that? Any questions? All right. Well,